Lesson 10-4, Arcs and Central Angles. A central angle is an angle with its vertex at the center of the circle. With an arc being part of the circle, angle ACB would be a central angle. Arc AB is measured in degrees and is equal to the measure of angle ACB. So let's look at these types of arcs. On the types of arcs, if you look in the middle, what you're seeing here is your semicircle. And if you remember, anything smaller than the semicircle, like arc DF, would be a minor arc, and anything larger, like KNM, would be a major arc. So when we talk about the measure of arc DF, since this angle right here is a central angle, this would be equal to the measure of angle DEF. For angle GJI, or arc GJI, that would be the same as the measure of angle GHI, which we happen to know is 180 degrees. For arc KNM, we would need that reflex angle, which we can calculate by finding 360 degrees minus the measure of angle KLM to find the measure of that reflex angle. The measure of a minor arc is equal to the measure of its central angle. The measure of a major arc is 360 minus the measure of its central angle. Now let's look at our congruent minor arc theorem. This states that two minor arcs are congruent if and only if their central angles are congruent. So our first example wants us to find the measure of several arcs and angles. So let's look at what we know. The measure of arc AB, because AOB is a central angle, will be the same as its central angle. So this is going to be 65 degrees. The measure of angle BOC, so BOC would be this angle right here. Again, that's a central angle, so it's going to match its arc. This is going to be 90 degrees. The measure of angle CDA, or arc CDA, we're looking for this. That is a major arc, so we're going to have to do 360 degrees minus the other side. So we're going to do 360 minus 65 plus 90, and this is going to give us 205. So measure of arc CDA is 205 degrees. The last one here is the measure of angle CAB, and so we're looking for this part right here, arc CA. Oh, I'm sorry, I'm backwards. For arc CAB, we have to start at C, go through A, all the way around to B. If you notice, this includes all of the circle except for that 90-degree region. So to do this, we would do 360 minus 90, and this is going to be 270 degrees. All right, let's take a look at example 2. They want us to find the measure of arc DE and arc ACD. Well, if we look at this, they've given us measures of all the arcs except for DE. But we know that all the arcs have to add up to 360. So we can add the pieces that we have, 120 and 42. We add these up, we're going to get 339. Then we're going to do 360 subtract 339, and we're going to get 21. That means this has to be a 21-degree arc, so the measure of DE would be 21 degrees. To do the measure of arc ACD, we would need to add together the appropriate arcs. So we're going to start at A, we're going to go through C, and stop at D. So for arc ACD, we're going to add together 55 plus 120 plus 42, and we're going to get 217 degrees. So now let's look at our clock examples. This is a very typical application of angle measures. So let's think about what we know about a clock. We want to know the minor arc measured by the hand and the minute at 2 o'clock and at 10:30. So let's start with 2 o'clock. We think about this. Here's my center. At 2 o'clock, the shorthand's going to be pointing at 2, and the longhand's going to be pointing at 12. The easiest way to think about this is breaking the circle up into 12 congruent segments. And this has covered 2/12 of the whole circle, which we know is 360 degrees. So when we simplify this, we're going to get this to be a 60-degree angle. So now let's go look at this for 10:30. This is a little bit different, so let's sketch a clock. Okay, so let's pretend like this is a nicely drawn clock with everything the same distance apart, and let's think about where 10:30 would be. Well, we know that the 30, so our long hand, our minute hand, is going to be at the 6. 10:30 is halfway between 10 and 11, so our shorthand is going to be halfway between the 10 and 11. So this is going to cover 1, 2, 3, 4 and a half twelfths of our circle. So if I look at this as 4 1/2 twelfths of 360 degrees, I can take care of this arithmetic and find that this is 135 degrees. Our congruent arcs theorem says that in a circle or two congruent circles, two minor arcs are congruent if and only if corresponding chords are congruent. So in our case, that would say that arc AB is congruent to arc CD if and only if segment AB is congruent to segment CD. For congruent chords theorem, in a circle or two congruent circles, two chords are congruent if and only if they are the same distance away from the center. So what we're talking about here are these two distances. So we're saying XE is congruent to XF if and only if AB is congruent to CD. Our perpendicular radius theorem, and yes, that should have an I in here, says that a radius bisects a chord and its minor arc if and only if it is perpendicular to the chord. So what we're seeing here is if this is perpendicular, then we know that AE is congruent to BE, which makes these two congruent. We also know that arc AG would then be congruent to arc BG. So these two arcs would be congruent. So let's look at example 4. They tell us that a circle with diameter of 20 centimeters has a chord located 8 centimeters from the center. Remember that distance has to be the shortest distance. To be the shortest distance has to be perpendicular. We want to find the length of the chord. So let's sketch the situation here. Here's our circle with our diameter of 20 centimeters, which would mean that our radius would be 10 centimeters. So if I have a chord that's 8 centimeters from the center, that means this has to be a right angle. This is 8, which leaves this part to be 2. I can draw another radius connecting the end of that back to the center, and I know that this also has to be 10, because if my diameter is 20, I know that my radius is 10. This gives us a nice little right triangle to solve. It looks like this. We have 10, 8, and then we can find the length of half of that chord. So we can set this up, x squared plus 8 squared equals 10 squared, or better yet, you can notice that those are both multiples of 2 from our 3, 4, 5 right triangle. So if you're using your Pythagorean triples or solving it either way, you're going to get x to be 6. Now keep in mind what you just found is this length right here. They want the whole chord. If they're perpendicular, we know that those two are congruent, so then I know that my chord has a length of 12 centimeters. Now let's look at example 5. An equilateral triangle is inscribed in the circle of radius 8, and our job is to find the triangle's length. Okay, so remember that your circumcenter means that these these are going to be on perpendicular bisectors, which means if I go here, so I'm perpendicular to the sides of my triangle, those have to be the same length. This, my radius, is 8. So I can set this up. This is a equilateral triangle, so I know that these are all 60-degree angles, which makes these 30-degree angles. So if we look at our little triangle here, I have a 30, 60, 90 right triangle with a hypotenuse of 8. So if you remember, the side across from 30 is n, hypotenuse is 2n, and the side across from 60 is n radical 3. So if 2n is 8, then I know that n has to be 4. That makes this side 4, and it makes this side 4 radical 3. Now keep in mind what this is just half of our whole side of our triangle. So the triangle's side length would be 2 times 4 radical 3, or 8 radical 3 units. And our last example. Example 6 tells us that in circle O, the measure of arc RS is 70, and the length of RS is 20. We want to find the radius of our circle and round this up to 3 decimal places. Let's sketch this. Okay, here's our circle O. Our arc RS has a degree measure of 70. Our OS would be a central angle, so I can tell that this would also be 70 degrees. And the length of RS is 20. So let's pull this triangle out and take a look at it. What I have is a triangle with a 70-degree measure and a 20 unit side. Well, since these are both radii, I know that those are congruent, making this an isosceles triangle, which means these angles have to be congruent. That will help me find those. Subtracting from 180 gives us 110. Divide that in 2, and we find these to be 65-degree angles. Still, we need a little more information here. So let's drop a perpendicular straight down here, which means this is going to bisect this side, making each one of these 10. Now I have a right triangle that I can pull out with a 55-degree angle right here. This is the side we're looking for, and I know that this is 10. So using trig, this is my hypotenuse, this is my adjacent side, and this is the angle I'm looking at. Adjacent and hypotenuse means that we need to use cosine. So cosine of 55 would be adjacent over hypotenuse, multiply by x, and divide by cosine of 55. And this is what we have. And we can type this into our calculator and find x to be approximately equal to 17.434 units. Okay, this was the end of the video. At this point, you should go do your Tier 1 and your knowledge check.